Greetings everyone, my name is Praveen Raj Ravi. So here I'm presenting my final year project, which is a design and development of SIW cavity bandstop filter. So this project will act as a bandstop filter which is trapping a specific frequency. So for my project, I've chosen 3.5 GHz to trap frequency. So why I'm choosing 3.5 GHz? Firstly, high loss in 5G application. The wideband and ultra-wideband is widely adopted for 5G globally, resulting in high signal loss in long distance and also low bandwidth long distance, but it giving us low data rate. Also, it affects the high radiation loss. Secondly, most recent SIW filter research focuses on bandpass designs, and also there is a limit focusing on bandstop filters, especially targeting specific frequency for 5G like 3.5 GHz. Also, one-port network gives us more radiation loss. And then we have offering the SIW, which is substrate integrated waveguide filter, to low loss and then easy integration, and also the compact size to make them suitable for 5G front-end modules. So the main objective for my project is to design and simulate a cavity bandstop filter for trap 3.5 GHz frequency, and also I need to analyze the cavity bandstop resonance response using S parameters. I have used a rectangular waveguide to SIW microstrip line transition method for my project. So firstly, I've designed the rectangular waveguide using air filling. So I prefer the parameter using rectangular waveguide table for S-band frequencies. Secondly, I have insert the FR4 substrate and also reduce the parameter according to the dielectric constant of the substrate. And then thirdly, I have reduced the thickness of rectangular waveguide according to the substrate thickness, which is 1.6 mm. And then I have designed the bias, which is 0.3 mm diameter, and also with the pitch of 0.45 mm. Fifth step is I have removed the side walls and it will become a SIW's basic microstrip line structure. And then I have integrated the feeding line and also the taper line. As a final step, I have designed the cavity bandstop resonator, and also I have followed the length of cavity bandstop resonator with the actual width of SIW. I have done several analyses for my project. So from there, I have choose the most precise result. So we can separate into two categories, which is the resonator coupling and also the resonator placement. So in resonator coupling, there are three types of couplings. The first one is undercoupling. In the undercoupling, we can say that the result doesn't enough the proper transmission coefficient, which is it cannot reach the below 20 dB. We can name it as undercoupling. So the second one is overcoupling. Overcoupling is fully opened vias. Fully opened vias is like the vias between the width between the resonator will be fully opened. So whenever the vias fully opened happen, the reflection power will be too weak, but the bandstop response will be so powerful. It's like below 40 dB. Thirdly is critical coupling. Critical coupling will happen when there is enough size, length of iris, and also the S parameters resulting, the S11 will be reflected more powerful, and also the transmission coefficient will be trap the 3.5 GHz signal properly below 30 dB. Besides, we go for the placement of cavity resonator. So firstly, I have tested in centered of SIW. So When we place at the center of SIW, it will trap the signal of mid-band frequencies. So now we are running between the 2 GHz to 4 GHz. So it will be trap the signal in between 3 to 3.5 GHz. And lastly, we go for the side-placed cavity bandstop resonator. So it will be placed at side of the SIW. So now it will be trap the signal at the starting frequency or the ending side of the frequency. So from here I can conclude that the center placed with critical coupled SIW cavity bandstop filter is more efficient for 3.5 GHz. Moving on to innovation. The complexity of the project lies in the planarization of high frequency physics. Traditionally, achieving high quality factor, which is Q filtering, required bulky, expensive metallic rectangular waveguides. So in my design, innovates by replicating that same electromagnetic performance within the standard 1.6 mm of FR4 substrate by precisely calculating the via diameter of 0.3 mm and a pitch of 0.45 mm. So we create a synthetic metallic wall that prevents radiation leakage. This offers a superior balance of quality and miniaturization compared to previous bulky designs, making it ideal for the high density requirements of 5G hardware. Sustainability is at the heart of this design. We align with the SDG9, which is Industry Innovation and Infrastructure, by enhancing the reliability of 5G mid-band networks through the better interference. We align the SDG 12, which is Responsible Consumption. So unlike traditional waveguides that require heavy metal casting, this filter uses standard recyclable FR4 glassy epoxy, which minimizes manufacturing waste and also uses few raw resources.
Our design criteria was strict. The filter had to be compact, low profile and high selective. We achieved a total length of 95.33 mm and kept the reflection levels below -15 dB to ensure the maximum power efficiency. So the potential application are vast. The filter is perfect fit for 5G base stations, specifically for the N78 band used globally. Finally, let's discuss about marketability. The most significant competitive advantage here is cost efficiency. Traditional waveguide filter can cost hundreds of dollars due to precisation machine. My SIW design has an estimate material cost of only RM50. Furthermore, because it using standard PCB fabrication, it is factory ready for mass production. Industry can integrate this directly into their existing production lines without investing in new machinery. High performance at a low cost makes this a highly marketable solution for the global 5G infrastructure market. To conclude, while this project successfully validates the 3.5 GHz SIW bandstop concept, there is a significant room for expansion in PSM2. So my future work is, firstly, I plan to transition from a single stage to a 3-stage bandstop filter. By cascading multiple resonators, we can achieve a much deeper rejection level and a broader stop band to better protect the N78 spectrum from high power interference. Secondly, I will proceed the fabrication phase using the FR4 substrate to verify the simulation result against the real world hardware.